Okay, shall we get started? So we're very pleased to have Omer Offen from Brandeis, who will tell us about period integrals of automorphic forms and the residue method.
Thanks, David, and thank you for this event and for inviting me to speak here. The entire ongoing event is introducing us to some new perspectives on the relative Langland program. And admittedly, I'd very much like and hope to learn from this event about this new perspective, but I'm not at the point to say anything intelligent about it at the moment. So what am I doing here? Well, you can sort of see me as your hands-on man in the field for period integrals of automorphic forms. For me, the relative Langland program is trying to study relations in period integrals, images of functorial transfer, and special L values. What I'd like to sort of do today is go over some well-studied examples, discovering these relations, and then talk about some new constructions. So in order to sort of set up things, I don't want to be too technical and introduce much notation, but let me just tell you what I mean by period integrals in this context. So we fix a reductive group over a number field or function field if you want, and subgroup and automorphic forms on the group G, right? So let me first maybe, so I think in some of the talks, the introductory week, we've already seen the bracket notation for the space of the automorphic quotient, right? And automorphic forms are periodic functions on the adelic points of G over the number. So if I'm considering an automorphic form, that's it's a periodic function on G. If we restrict it to the subgroup, the adelic points of A, it's also periodic, and then we can try to integrate, right? So the period integral and if the automorphic form you start with is a cusp form, then this integral makes sense. It's a convergent integral, and we're interested in whether or not it's zero. It's currently related with functorial lifts, and if it's not zero, it has a value, and often this value is related to special values. If it's not a cusp form, this integral needs not converge, but may still be of interest. And in this program, there are a lot of physicists. We know that there is a meaning to non-convergent integrals. And we are trying to make sense of this integral when it doesn't converge as well. So I will discuss some possibilities for regularization every time. So let me tell you what we know in the context of cusp form, periods of cusp forms in some special examples. And the first example I want to discuss is called unitary periods. So here, the group G is the general linear group, but over a quadratic extension. Considering a quadratic extension of the number field, and G will be the group. So the identity points of G are really GLN of the adels of V, and H will be the n-dimensional unitary group with respect to this quadratic extension. So let's say, I mean, there are choices of Hermitian forms, but let's say we choose the one where it's the quasi-split one, just for the sake of the introduction. So this example was one of the sort of first general rank examples that was understood in this context of relation with the factorial leaf. Maybe just before stating the theorem, let me tell you what the factorial transfer is that is relevant to these periods. So the factorial transfer is quadratic base change. All right, so base change was studied much more generally. Cyclic extension was established by Arthur and Bolzell in 1989. And basically, it's a transfer from automorphic representations of ln over f to automorphic representations ln over E. And there are many ways to characterize it. So let's say we'll denote by the base change of phi prime the representation of GLN over E that transfers from, so phi prime maps to phi. Let's call this map the base change map. It can be defined in terms of a character identity. It has a local counterpart, and the local components are also correspondent under base change, the local base change. One way to characterize this map is in terms of L functions. So the L function of the base change is the product of L functions of the pre-image phi prime, and it's twisted by the, so there is a unique quadratic character that is associated by class field theory to quadratic extension. Okay, and you know, basically the Dedekind zeta function of Q joint I is a product of the Riemann zeta function and Dirichlet character with conductor -4, so that's sort of the generalization of this. And that identity basically defines the map, characterizes. So the work of Arthur and Bolzell is based on the trace formula, and they also actually characterized the image of this transfer by, so I is a base change. With a non-leaf, it is representation which is invariant by the Galois.
Sorry to interrupt. There's some request if you could write a little larger. Write pretty large, but
I'll try.
With,
We'll try.
Maybe it's a resolution issue. That's beyond your.
So the relation with is discovered by Jacquet. Jacquet proved that. So if we consider any Pascal irreducible automorphic representation of G, and I is a base change if and only if the unitary period restricted to pi is not identical to 0. So non-vanishing of periods captures or detects the image of period transference of the quadratic base change to this. So the results of Jacquet are based on what he called the relative trace formula, and actually, so it's a tool developed to study such period integrals and characterize transference in terms of non-vanishing. And it was maybe sort of a first general rank case that really we don't know how to prove without the relative trace formula. And we studied further these period integrals for general unitary groups and related their values to special values of L functions. So we also characterized for a general, not necessarily quasi-split unitary group, the non-vanishing of the period, but just to relate with special L values. So if you consider, so this is the after it well, sure. So we showed that the unitary period of a cusp form normalized by the L2 norm. So here P is in the base change of some pi prime. That this value is related to the following quotient of L function. So it's the Rankin-Selberg L function, but not of the representation itself, but its free image under base changed, twisted by this quadratic character over the value of the L function F1 without the twist by era, but that's whole of the L function. So it's really a residue at S equal 1 of LS. Right? And it's this will direct. So it's not really an equality. It's almost everywhere equality. And it's depending on some, so up to some ramified data. I want to quickly mention just one more such example.
Can I ask a question?
Yes, please.
In the case of GL2, isn't it, I mean, the SIL function that plays a role with respect to, I mean.
So the SIL function more naturally comes in when the period subgroup is GL2 over F and not the unitary group.
Okay, yeah, GL2 over F, right.
Yes. Okay. And the functorial transfer that then plays a role is base change from the unitary. So yeah, it's kind of a dual situation.
Okay.
This L function?
Question, you said something.
The aside L function, so it's a twisted tensor L function. Thank you. So Friedberg and Jacquet studied the following case. So their theorem says that high and irreducible Aspidor representation of GL2n, then the GLN cross GLN period restricted to pi is non-vanishing if and only if the following two conditions hold. So the L function of chi at the center of symmetry is non-zero, as well as the symmetric square L function has a pole at 1. Right? So they directly related this period integral to the product of two L values. So without sort of sophisticated methods like the relative trace formula, it is hard to put hands on non-vanishing of period integrals for Aspidal automatic representations. But there are some situations when we really just don't have non-vanishing periods of cut forms. I want to talk about such examples. Things. These are such that pH restricted to all the cusp forms on G, just identically zero. No cusp form has a non-vanishing. So there is a sort of a trivial example, which is not very informative, by taking H to be the unipotent radical of a parabolic subgroup. You basically reconstruct the definition of cusp forms once. But other examples have been established. So for GLN, so let's see, stable G and H. If you look at these period subgroups GLK and GLN minus K, but in the case where K is not N minus K, that's a vanishing pair. GL2N and the symplectic group is a vanishing pair. And the symplectic group and the product of two smaller symplectic groups. So if you have a symplectic form, you can decompose it as a direct sum of two symplectic forms, and the product of SPs is the subgroup that preserves this decomposition. And so here there are no restrictions on K and N. These are all vanishing pairs. So you cannot find cuspidal representations where the period vanishes. And the question is, even a pair of G and H, find automorphic forms on G such that they carry a non-vanishing. Of course, there is one very simple way to do that. Just take the constant function 1, integrate over H, you get the volume of H. But in some sense, this is true for any subgroup H, but the group H being G, the entire group, is really the group that detects the trivial representation. Tells you this is the only non-vanishing. So maybe the finer question is, what we think is detected? By the H period. So if you're in a situation of a vanishing pair, you can't really look for cuspidal representations. And then you can start going to the spectral decomposition. So the L2 space of G decomposes first as the discrete spectrum and the continuous spectrum. Okay. And the continuous spectrum is basically constructed of Eisenstein space. And these are sort of more hands-on objects that we can try to compute with. And then the discrete spectrum, well, it decomposes further as the cuspidal spectrum, and anything else can be constructed as, so Eisenstein series, write some notation in order to say something informative about their periods. They come in sometimes multivariable families of parameterized by complex parameter of automorphic forms. And they depend meromorphically on these complex parameters, and you can take multi-residues. And it turns out this is part of Langland's spectral decomposition, that every discrete automorphic representation that is not cuspidal comes out in this process as a residue of an Eisenstein series. So that's where we are going to try to find automorphic forms with non-vanishing. But let me just remark something about Eisenstein series and period. So what is an Eisenstein series? You start with a parabolic subgroup. Let's say with Levy part L, and let pi be an automorphic representation of the Levy. So the Eisenstein series can be viewed as it's an intertwining operator from the induced representation, parabolically induced from P to G of pi, and think of it as twisted by this complex parameter. I'm not going to explicate it. Essentially, you can think of it as lying in the dual of the complexified Lie algebra of the center of the Levy of P. So one can twist pi by lambda and then induce to G. And it's just an intertwining operator into the space of automorphic forms of G. Okay, and an explicit way to define it, if you choose a section in your induced representation, evaluate the series summing over rational points in G mod P, be twisted by lambda gamma G. And this series converges if lambda lies in some positive cone, and then it has a meromorphic configuration for all parameters lambda considered as a meromorphic function. So let me just mention the following very informal remark on the formal unfolding. So if you write down formally the period integral of an Einstein series. So we have an integral over the automorphic quotient, the Delic points mod rational, of a sum of the rational points of G mod P. You can break this sum into double cosets with respect to age. And then for every age, there is a stabilizer by the double coset representative. So you get an integral. So you can sort of the unfolding will look like a sum. These are rational points, but I'll just write the double cosets like this. Let's say eta is my representative, and then an integral for Delic age mod rational stabilizer for that representative of 3 lambda eta h. Now, I'm putting a quote by quote on this equality because there is no reason for any of these sites to be well defined. These are not convergent integrals in general. Typically, for these type of integrals, they will factor through an integral over R of an exponential, for example. But this unfolding process is actually turns out to be very informative to indicate to us where to search for non-vanishing periods. So an ideal picture, when we can get an information from this formal unfolding, is when we know the double coset space very well as the stabilizers. And we observe that for most summons here, well, this integral will factor through a period integral for the inducing data I. So if most stabilizers are subgroups of the Levy which form a vanishing pair, and your data is cuspidal, that would be automatically telling you that many of those summons should not morally contribute. So in an ideal world, you will get a single contribution, and you will know this single contribution for some other reason is non-vanishing. And even though this a priori has no mathematical justification, it's a great indication to look for examples. And the examples that I'm about to discuss, that's the way they were first discovered. So the first example of a non-vanishing discrete period that I want to discuss is the construction of Ginzburg Rallis. And Sudri from right? And so for the rest of the talk, I will really just think about the case of G being the symplectic group. For their example, you can even rank symplectic group and consider the subgroup SPM process. So the construction goes as follows. So let pi be an irreducible Caspilon automorphic representation of GL2N that satisfies the following properties. So the property is that the Friedberg-Jacquet period is non-zero. So L pi at 1/2 is non-zero, and the exterior square L function has a pole at S equals 1. And then, so GL2N is the Levy subgroup of the Ziegel parabolic of G, SP4N. So we view pi as a representation of the Levy subgroup, of the Ziegel Levy subgroup of G. Then we consider its induced representation from the Ziegel Levy, from the Ziegel parabolic into G of pi twisted by complex parameter S. Let me call this Eisenstein series E naught. This figure. The theorem is that the Eisenstein series E naught admits a simple code S equals 1/2. And if you consider the space of residues that is spanned by taking residues of all these Eisenstein series, so the space that I will denote by discrete E residue S equals 1/2 of this Eisenstein series forms an irreducible automorphic representation in the discrete spectrum of G. So this is this construction of hands-on construction of a residual representation as a residue, an Eisenstein series. And it shows up in a bigger project of Ginzburg, Rallis, Sudri, constructing of a construction called the descent that is trying to find sort of the inverse of the functorial transfer from classical groups to GLN. And so this result is just about the discrete spectrum. It has nothing to do with periods. But then they've also discovered that this construction is characterized by a period, by exactly this period subgroup, SPN cross SPN. So they proved the second part of the theorem that SP2N cross SP2N on this residual representation is, well, first of all, now it's not a Casimir representation, so it's not automatic that this period integral is defined by a convergent integral, but so it is convergent. And it's not identically zero. So maybe sort of towards the end, I will explain the method, but I just want to say one thing about the sort of final result that they get is that, so one can define the following integral not on the residual representation, but rather on the induced representation. If you take an element in the induced representation, you can take an integral over the maximal compact of H. And then the Friedberg-Jacquet period, sort of on the inducing data. This is just some linear functional defined on the induced space, but in fact, if you look at it as a linear form on the induced space from S equals 1/2, this linear form is H invariant. So H being the period subgroup SP, 2n cross S2. And furthermore, it is non-zero because of the Friedberg-Jacquet characterization. But that's just on the induced space. And the result that they are actually proving is that the period integral of the residue of the Einstein series equals this linear form on the section. So in other words, we have this map. We have a map from the induced at 1/2 to the discrete spectrum, and the period integral complements this diagram, completes this diagram. It means that this linear form factors through the residual representation, and it is exactly the period integral. It's the diagram. And that's how we get the result. Now, if you remember the formal unfolding, this is exactly the one term that contributes to this formal unfolding. And that's how it predicts result. So maybe one more remark about our example. So it can also be shown that if we're looking at the period with respect to the other products, S4 and minus K, restricted to this representation is identically zero. So amongst these family of subgroups, of period subgroups, SP cross SP, it is exactly the equal case that detects this transfer, this construction. So based on the Ginzburg-Rallis-Sudry construction, we generalize this construction to generate residual representations of symplectic groups that will have periods with respect to these subgroups in the unequal case. That's what I'm going to discuss next. So what is the newer construction? So it is convenient to parameterize a symplectic group as SP4N plus 2M, and M will now be strictly positive without but the M equals 0 case. And the period subgroup will be SP2N plus M plus SP2M. You see, this is a general situation of a symplectic group and a product of two symplectic groups. It's just a convenient way for us to parameterize it. And we start with an hospital automorphic representation on GL2N is exactly the same, satisfies the exact same conditions as in the Ginzburg-Rallis-Sudry construction, the one that has a non-vanishing Friedberg Jacquet gradient. But now the Eisenstein series that we're considering starts with an induced representation into G. So from the parabolic subgroup, so G is SP4N plus 2M, and we take the parabolic subgroup that has a Levy component, which is isomorphic to GLM plus SP4M. And the inducing data that we're using on GLM is just the trivial representation. So the complex twisting parameter will just give absolute value determinant BS, while on the SP part, we take the discrete representation that showed up in the Ginzburg, sorry, not of pi, the discrete representation that showed up in the Ginzburg-Rallis reconstruction. So for every such representation, element in the induced space, now there is an associated Eisenstein series. And so one thing I want to point out that creates a lot of technical difficulties for us is that this Eisenstein series is no longer, the inducing data is no longer cuspidal. So for us, what that means is that it's asymptotic. It's a lot more complicated to study. There are many more constant terms that are not vanishing. That creates a lot of difficulties. So the results that we have obtained are, in some sense, the analogous results. Maybe before stating the result, there is an analogous linear functional. So let me define it. So Lm is now integral gain over the maximal compact of the period subgroup H. And now the inner period subgroup is a subgroup of just SP4N. It's the period subgroup of Ginzburg, Rallis, and Sudry. And again, it is easy to see that, well, so Lm, if you just look at the induced space from, right, so it's that at S equals M plus 1 over 2. It's H invariant. And it is non-zero. And the non-vanishing is because the inner period is non-vanishing because of the previous results we discussed. So again, we show that, first of all, at this point that the formal unfolding predicts a non-vanishing, we actually get a discrete automorphic representation. So the space again spanned by red. Oh, so maybe I should check firstly. So yeah, Eisenstein series has a simple at the point n+1/2. And the space spanned by residues call it EM5. Forms an irreducible representation of the automorphic spectrum, the discrete automorphic spectrum. So we have a new construction of a residual representation. And the second statement that we prove is, again, we have a projection from the induced space at n+1/2 to the discrete spectrum. And we're saying that the linear form LM, the age invariant linear form, factors through this projection. Factors. Through. So in other words, we have this projection here. And so the diagram can be completed. In other words, M5 means an age invariant linear form. Now, the reason I'm being a little bit more careful here and not stating it is the period integral is because on this example, pH fails to converge on these discrete representations. We're in a situation where we don't have a convergent period integral to talk about, and the theorem allows us to build a regularization. So in the time left, I want to say a few words about how all of these theorems I mentioned about the residual spectrum periods of the residual spectrum are proved. And the main tool is the so-called residue method. And it was a method that was introduced by Jacquet and Rallis in one of the vanishing pairs examples that I wrote down, the GL2N and SP2N. That was the first example where they constructed representations with non-vanishing periods which are not cuspidal. And Ginzburg, Rallis, and Sudry did the complete analog of what Jacquet and Rallis did in their work to show that their period is non-vanishing. And the idea is, well, the period of the Eisenstein series is not well defined. Let's cut off the Eisenstein series and make it a nicer analytic function so that we can well define the integral. And the tool they've used, the prototype of cutting off that was available, was Arthur's truncation operator. So I don't want to, again, this is a truncation operator gets quite technical, but the device introduced by Arthur is basically, so you take an automorphic form, and the standard notation is you form its truncation in, well, T is not just for truncation, it's a truncation parameter, right? So the truncation, the T truncation of P, so that's basically a process that takes any periodic function on G, let's say with uniform moderate growth, and it transforms it to a periodic function of rapid decay, well-behaved periodic function. So how is the process done? Again, I don't want to write down the precise definition, but let me just tell you what the form looks like. So you average over parabolic subgroups, or not average, but take an alternating sum. And what you do, well, what measures the asymptotic behavior of an automorphic form along its, so the boundaries are the parabolic subgroups, and what measures the asymptotics is the constant term along these parabolics. So you take constant terms along these parabolic subgroups, but you cut them off. So there is a cutoff function depending on this parameter T. But when you do this process, you lose automorphicity, you use periodicity. So you average over G mod P in order to regain periodicity. Okay, but actually for this G, this sum is a finite sum. So you don't lose the asymptotic, the nice asymptotic behavior. And as T goes to infinity, you approximate your automorphic. Okay?
So T is just a positive real number or something?
So if you're in a situation where you're rank 1, T is just a positive real number. Otherwise, it lies in a cone inside a finite dimensional vector space. And you just, T goes to infinity just means along the cone. So both in Jacquet Rallis work and Ginzburg Rallis-Sudry work, well, now they have a rapidly decreasing function. You can the truncated Eisenstein series. You can compute its period. It's well defined. So you can try to do the unfolding for real. Well, the fact that you have an integral of a sum that converges doesn't mean that you can swap. So they worked really hard to prove convergence of many terms that are morally zero. There was a lot of work to prove that something is zero. So a little bit later on, this notion of truncation related with period integrals was thought about more conceptually. And Jacquet, Lapid, and Rogowski introduced a variant of Arthur's truncation that fits a lot better to the context of period integrals. So that's the gadget that we have used, and really for more complicated Eisenstein series like the ones we considered, trying to use the sort of older methods would have been impossible. The computations that come up are just impossible to have control on. So you really need this better suited truncation operator. Relative more mixed patient. So it was introduced by Jacquet and Rallis. So they introduced it only in the case where age is a symmetric, is a Galois symmetric subgroup. It's a fixed point of a Galois involution on G. But it was defined more generally, much more recently by Michael Zidor. Whenever H is reduced. Not quite general. Okay, but the ideas are all in here. It's just a matter of studying better, basically, more general setups of cones inside the vector spaces, not just affine code. So why is it called mixed? Well, you want to study something that instead of taking you into rapidly decreasing functions of G, all you really need, you want to integrate over H. So instead, you want to end up in rapidly decreasing functions on H. And for this, you just change the averaging instead of G mod P to be H mod P intersect H. So this is the general form, but I mean, one could potentially also think about taking constant terms for parabolics inside H. But when you take an automorphic form on G and you don't take its constant term with respect to parabolic subgroups, you're losing all the finiteness properties of automorphic forms. So it would really be an unnatural object that is hard to put our hands on. And so the mixed means you take actual constant terms for G, but you take averaging just for H. So this gadget brings you into periods. So now one can talk about the period of a truncated Einstein series. This is a well-defined object. And in Zidor's work, he actually built up a machinery that automatically gives you the upshot of the unfolding. You don't need to go through the process of proving convergence for each term. It comes from combinatorics cones, basically, and their Fourier transforms. Really. So what we studied is the period of this relatively truncated Eisenstein series, and we just computed the limit as S goes to m plus 1 over 2 in order to get the result. I think that's a good place to start.
So can I ask a question?
Yes, please.
So these papers that Pollack and Van and Zidor wrote, are your cases? I mean, how are they related? It's a subset of their, is it intersection or?
So all of the cases that they considered, like the cases that Jacquet and Rallis and Rallis, Ginzburg, Sudry considered, they are all cases where the Eisenstein series is induced from a maximal parabolic and the inducing data is cuspidal. And for those representations, there is only one constant term. So this unfolding process of studying the period of truncation is become a lot simpler. Okay. And so our case is different. We start with a representation induced from discrete And we need to analyze constant terms along many parabolics and in order to eventually show that there is only one term that contributes. So that's where the sort of new complication comes in. In fact, what happens is that we cannot directly consider the isolates with just one complex parameter. We have to realize the trivial representation of GLM as a principal series and take a multivariable residue. And instead of just taking the limit, we have to take it in a very specific direction for our particular summand to be the only one that is not vanished.
Thank you. That's very nice. Thank you.
It's a very vague question, but the story that you're telling here, the general theme, does it have a local version that you can look at local harmonic analysis? So these vanishing pairs and that would kind of how do I detect them?
Yeah, so you're talking about in general age-invariant forms on local representation theory.
Yeah.
Yeah, so the methods are somewhat different, but and there's also a question of what should be the definition of a vanishing pair, because in the automorphic setting, it means vanishing for cuspidal. Is this really the thing you want for local representations? I'm not sure. And maybe you want tempered. Maybe that's a more reasonable object to think, or generic. I don't know. So, right, one needs to sort of think about what are the right questions. But yeah, we know a few things about examples and about the examples I mentioned in particular. But I don't know anything general.
Okay, well, let's thank Omer again for